welcome to today's panel looking at the RarePlanes dataset and case study. I'm Serge Patel, your moderator. Joining me today will be Thomas Hostler from AI.Reverie and also Jake Schermeyer from CosmiQ Works. Now, the aim of today's session is to give you the tools and strategies needed for you to start using synthetic data to augment your own real data training sets for your computer vision applications. Now, this session is live and all the speakers and moderators are online as I speak. You can say hi and also submit your questions in the chat window below. So with all of that, please enjoy and please do submit your questions. We are here to empower you with the knowledge you need to start using synthetic data. And with that, I'll cue for Jake and Thomas to introduce themselves and for Jake to do his overview of the case study before we dive into the questions. So take it away, Jake. Jake, could you please introduce yourselves and what you do?
Sure. Thanks, Serge. My name is Jake Schermeyer. I'm a research scientist with CosmiQ Works. CosmiQ Works is an applied research lab. We sit at the intersection of computer vision and difficult geospatial problems. And
Thomas.
Hi, Serge. My name is Thomas Hostler. I work as a computer vision scientist at AI.Reverie, a startup that focuses on creating synthetic data for computer vision applications.
Just to give an overview and a level set, Jake, do you want to take us through a quick overview of the whole case study and what we're going to be looking at and studying today, essentially?
Yeah, absolutely. So RarePlanes is a unique data set that combines both real and synthetically generated satellite imagery. It's the largest data set of its kind, and it's permissively licensed so that lots of people can use it, from commercial entities to academics to anyone sitting at home. The purpose of the RarePlanes is really to test the value of synthetic data, and our annotations in this case, we're really interested in testing the value of synthetic data for detecting aircraft from an overhead perspective, and also their features. So things like the number of engines the airplane has, the shape of its wings, really much more challenging aspects of aircraft detection. And one of the coolest things about RarePlanes is that it's hosted on AWS S3 for free public download. So AWS courteously invited us to join their open data program. So that means you can go download this data set today and play with a really cool mashup of real and synthetic satellite imagery. So the RarePlanes data set is expansive. It covers a very broad area. So if you look at this image on the right, we can see all of the locations in blue for the real data and the synthetic locations in red. Overall, we have 253 Maxar Worldview 3 satellite scenes across 112 locations, 22 countries in total. About 14,700 aircraft here and over 2,000 square kilometers of labeled area. The synthetic data created by AI.Reverie and their unique platform features over 50,000 images and 630,000 aircraft with a simulated total area of about 9,000 square kilometers. So very expansive. The different imagery products here, we're working with real data. We have Maxar Worldview 3 sensor. This is the highest resolution commercially available satellite imagery that you can purchase. So really excellent high quality data here. The corresponding synthetic data also has a similar spatial resolution of around 0.3 meters and also similar wavelengths. And finally, the look angles here are really quite diverse, ranging from about 3 to 30 degrees for both the real and synthetic data. So on this slide here, we've got 4 rows of data, the top 2 coming from our Maxar satellite and our real data set, and the bottom 2 created through the AI.Reverie synthetic data platform. And what I really want to draw attention to here is how closely and how similar these data sets really are to one another, and how great of a job AI.Reverie did at simulating actually real satellite imagery. The other thing I want to point out here is the diverse background conditions that are prevalent in both the real data and the synthetic. So we've got snow cover, various types of background. And the AI.Reverie software really enables you to create any type of weather condition in any location. So if you want to make it snow in Miami, you can do that. If you want to change the backgrounds to make it dirt runways in LAX, you can do that too. So this really increases the diversity of the data set and should help improve generalizability of computer vision algorithms to new areas.
So the experiment presented in the paper focused on two different areas. So the first one is aircraft detection and classification of the roles, and the second set of experiment focused on just pure detection of aircraft. And so this slide is presenting our results on these two sets of experiments. And so for each set of experiment, we ran different trainings of models. So we first train on the real only dataset. So we train a model only on the Maxer images. Then we also train models on the synthetic dataset. So these 50,000 images that we generated using the airport simulation platform. And finally, we used a transfer learning method, and we were interested in the performances of the model using only a subset of the real data. And so the results reported are the mean average precision and the mean average precision 50. And so what we can see here is, how first of all, I think that the first takeaway of this slide is the performances of the synthetic data set only. So by only using synthetic data set and not using any real world data set, we are able to train a model that is that can detect and classify aircrafts. And so I think by itself is a really valuable result. Even though the performances are, slightly below the real only models, we are able to create a model that is like detecting and classifying aircrafts. And so that's, I think, in my opinion, is a really important takeaway and shows the value of synthetic data. And the second takeaway, and I think it's very interesting, is using 10% of the real data to fine-tune a model that has been trained on synthetic data only. And so by doing that, we are hoping that by training this model on synthetic data and giving it only a small subset of real data, we are able to improve the performances significantly. And so that's what we've been observing. That's what this bar chart is showing, is that only using this small subset of the real data, we are able to obtain performances that are almost on par with the model trained on real data only. So if you are able to create a synthetic data set and only label a very small subset of real data, then you can create a model that has really good performances. And that's basically what we are highlighting in the paper. And I'll let Jack take the next slide.
Sure, thanks, Thomas. So on this slide, we are really examining the value of synthetic data for the detection of rare objects. So in this sense, we're investigating when you have different breakdowns of training examples for each object. So we're looking at the x-axis here. So say you only have 10 examples of a certain type of object. What is the value of synthetic data for boosting your performance? On the y-axis, we have our performance metric, which in this case is mean F1. The orange bars here, we're using the 100% of the real data, and the green bars, we're using blends of synthetic and 100% of the real data once again. And what we really can see here is that a significant performance boost occurs when we start to add in the synthetic data and boost, that consequently boosts performance in these rare object classes, which is something that really hasn't been heavily investigated in the past, and something that you could potentially do with the RarePlanes data set as well. So we have several resources here that will be helpful for end users who want to investigate and dive into using the RarePlanes data set. We've created an excellent code base that will help you with the various pre-processing steps required for working with satellite imagery. And then we also have a detailed user guide, so it's going to walk you through all of the little minutia of the data set, so you can really use it to its full potential. You can download the RarePlanes data set off of AWS through their open data program for free. All you have to do is have an AWS account installed and configured. And then I just want to point out our two websites of our company. So AI.Reverie and CosmiQ Works, which this was a joint creation and joint effort to really produce this data set. And I think it's been an awesome collaboration. So if you want to learn more, you can email hello@AI.Reverie.com.
All right, so I'm going to now start with some questions that I have, which I'm going to ask, which I think the audience might ask you and stuff, and so have a little discussion. Now, the first one, as a programmer who knows enough, but not enough to be completely dangerous in this situation, why did you guys pick planes? Why not pick something simpler like cars or soft drink cans? I mean, for example, why complicate life here?
Sure.
Okay.
Yeah, I mean, aircraft were just a really attractive object to go after, simply because, well, there's not any real data sets out there that exist that focus only on aircraft from an overhead perspective. So that's one reason. The second reason is there's all of these interesting attributes that you can label on top of them and really use that to explore the value of synthetic data for different tasks. So if we want to detect what the wing shapes are of planes or the number of engines it has, and then combine these together, you can really create incrementally more and more difficult and challenging problems. And that's really why it was an attractive option for investigating the value of synthetic data from an overhead perspective.
Now, just to explore that aspect a little bit, like the challenge of the data set and stuff. I mean, from my perspective, from what I could see is like satellite images are very grainy. They're in pretty low resolution. And given that, most of the time there's clouds on the planet, I mean, it must take a while to gather. So how does that affect the timescale of data acquisition?
Yeah, I mean, cloud cover is certainly a real challenge when working with satellite imagery. I think a lot of models are trained really to find objects in cloud-free data. It's, finding objects through clouds is something that could be really valuable, or haze. And when we bring in the synthetic data and be able to create some level of cloud cover, we believe that should actually help improve the robustness of models and their ability to really work in diverse weather conditions. And that's something we wanted to really test here. And I think we were able to successfully do that with the diverse weather conditions featured both in the synthetic data set and also in the real data set.
That's cool. Now, Thomas, you were one of the people that built the model, or the simulation. Can you talk a little bit about how you modeled actually the satellites as well and the sensors and how that affects it and its position? So you actually simulated not just the scene, but the planet and the satellites and everything, right?
Yeah, correct. I was actually not part of the team that created those synthetic words. I'm mostly like the end user.
It's okay. It's great.
No, but I would like to highlight, the work of my colleagues, all the technical artists at AI.Reverie that are able to create those really magnificent synthetic world. And so, it's a very long process, and there's like different level of involvement, different like person involved, and everyone is focusing on a different aspect. So, we start by, picking real world location and using, open data like OpenStreetMap, for example, and we're able to get building layout. And, from there, we are able to, we create the map of the airports, and we have then our technical artists that take it from there, and, they can add different models, and they start modeling like the vegetation, and they start modeling the different aircrafts that are flying through those airports. And on top of that, then we have a part of like animation as well, where we then model the aircraft flying through the space. So just parking and like going through the runway and like flying. So this is actually a very long process to model those airports, but then you are able to create a replica of this real world. There's a replica of the real world, basically, and then once you're able to do that, then you have full control on it, and that's where the value of synthetic data really comes, because you're able to control the weather, and you're able to control like every little detail of the world you created.
So related to that is a question that I have for actually both of you, Jake and Thomas. You're trying to spot aircraft which in many cases may only have 2 or 3 training images or 4 training images, etc. So can you just really explain or extrapolate really the value of creating an entire simulated universe there? And yeah, you're right, Thomas. It's a lot of work.
Yeah. It's certainly a lot of work, but I think it's something that could be really valuable. I mean, especially when you consider how expensive it is to collect these data sets. the real data that is, and being able to simulate these areas is really going to be a big cost savings. So if you're particularly interested in finding aircraft with 3 engines and a certain wing design, that's something that's going to be very helpful, especially if we can augment and create this synthetic data and then use that to really boost our performance in the real data set, where you might not be able to really go out there and purchase or know where these types of aircraft are in the real world.
Okay, great, and that's good. So when does a programmer know that they're going to need synthetic data, right? So I've got my data here. I've got 253 Maxar images. Is it just from my training results? Is it from the iteration? And I basically see that I'm not really getting the classification confidence that I want. And then do I look at it? And then, what do I need to know to even start looking for it? Thomas, maybe you want to?
Sure. So I think once you start looking at the distribution of the different objects that you have, you may realize that you need synthetic data, right? So let's say for these 250 Maxar images, and you realize that you only have a few instances of a particular airplane that you're really interested in identifying, right? And so the issue with real data is that you do not control the environment. So you're gonna gather the satellite images, and then you are hoping that you're going to get more instances of these particular airplanes that you really care about detecting. And so, hopefully you do, but like if you don't, then you need to collect more images and more images, right? But the cool thing with synthetic data is you actually control your environment. So if you realize that, this is an airplane that a type of aircraft that you really want to detect, then you can just increase the spawn probability of that particular aircraft, and then you're going to get a lot of different instances of that aircraft in your data set. I think that's really where synthetic data shines.
Okay, cool. Now, so Thomas, and actually Jake, for both of you, there's a lot of time and a lot of effort and clearly detail going into creating this model, right? And there's also equally a lot of effort and a lot of money in acquiring these images raw from the real world and then tagging them. Do you want to just, Jake, do you want to talk a little bit about where the cost is in tagging these images and in that process? And then where, to both of you, when do I decide actually it's worth me generating or getting synthetic images versus just sticking with what I've got and having it human annotated? Because the cost must balance up at some point.
Yeah, absolutely, Serge. So, I mean, satellite imagery, specifically this very high resolution satellite imagery, is very expensive. And, that's going to be a significant cost component. And then, just to do annotations on top of this, you typically need to have a specialized team that actually understands what they're working with satellite imagery. It's not something that you can just load into your average, ground-based, where you're going to label traditional photography and use it. So that these scenes are thousands, tens to hundreds of times larger than a 4K image. So that means covering a broad area. And beyond that, I think just having the expertise to be able to label different features of aircraft and the aircraft themselves is a challenging proposition, and you really need to have a team, and of course that's going to be expensive. So that's another added component. So I think everything in the geospatial domain is just a little bit harder than in the real world, and I think by adding in the synthetic data, that we can really hopefully start bridging that gap and reducing the burden, both financially and improving performance on the computer vision side as well.
And Thomas, do you think there's actually, at any point, is it the decision, is this about, accuracy has no price, or at which point is the 2% difference between training on, or the 1%, actually is 1.4% or something, at which point is that, at which point do you make the decision that it's worth the extra incremental percentage increase? Or am I framing the question incorrectly there? Is there something else?
No, I think it's very interesting. I would say it's like, depending on your application, right? If you are trying to kickstart a particular computer vision project, and you want to study the feasibility of an idea that you have, then you probably don't care as much about average precision, for example. But if you're working with self-driving cars, and we always talk about this like 99.999% of accuracy, then you want to get to that stage. And I think synthetic data by themselves might not be the solution, but it's definitely a great tool, and it's definitely a great way to like improve your accuracy, right? Because I think Jake highlight a very important point on the difficulties of annotating real world data sets, and the different layer of like QA that you have to go through, and the different costs and the time. And I think synthetic data can help bypass a lot of that. And also where synthetic data is really useful is it's providing example of rarely observed events, right? So if we get back to the self-driving car example, if you have cars driving through San Francisco for hours and hours, they might not observe a single accident, right? And so you can create synthetic data that would like help solve these issues. So I think really it's working together, right? Then as of now, synthetic data by itself is not the solution, but I think it really brings a boost of it can help solve some of the weaknesses of your real data set.
I mean, just training it on just synthetic data, it didn't seem to produce that bad a result. I mean, for many cases, many researchers out there, it may be the only solution, right, to actually create synthetic.
No, it is definitely true. It really depends on your application, right? And I think for a lot of cases, and for example, like airplane detection, right, if you mostly care about detecting airplane and you are not as interested in like those false positive, for example, you see that the average record that we presented in the paper, for example, is very high. So we are getting a very good result just detecting aircrafts. And so maybe for your particular application, that synthetic data is going to be enough. And in which case it's great. Like you should just use synthetic data because it's so much easier to annotate, for example. And especially if you work with like segmentation problems.
Well, just quickly, just for my geekery, is just very quickly a high-level overview of how that annotation data is generated in the simulation engine.
Sure. Yeah. For the real-world data, you mean?
For the simulation, the synthetic data.
Oh, for the simulation data. Yeah, so I mean, we don't have to do any of that. Basically, everything is automated, right? So what we do is we create those worlds, right? Those synthetic worlds and synthetic aircrafts, and then we select the camera position, and then based on that camera position, we take like snapshots, and the snapshots, it's very straightforward to extract bounding boxes because we know the object location and we know the object like dimensions, and it gets very straightforward to extract like high quality mask and bounding boxes, and it's a matter of seconds, right?
Got it. Of course. So you've got perfect information. You can basically just knock out the mask by turning them into the black color, or just highlighting them and then marking the data within programmatically.
Correct. There's no human interaction in it.
And so, Thomas, related to that is the question is how much is the cost difference between synthetic generated images from, say, from AI.Reverie and one that was like taken from a satellite and hand imitated? I mean,
sure. So depending on the type of computer vision task you're trying to solve, it can range up to several dollars for an instant segmentation task, of real data, right? Because it takes it can take up to like half an hour to an hour for a single image sometimes, especially when you are looking at segmentation task and large images like satellite data. As for synthetic images, the annotation cost is about 2 orders of magnitude less. So and it's the order of a few cents.
Now, gentlemen, I'm going to turn back to the data itself. Now, you said there were 10 attributes in the slide. Can we actually let's just bring that slide up quickly?
Sure.
And we can just discuss around it. Because I'd like to understand why so many attributes, and aren't you creating a problem with too much data then, or not?
I mean, I guess that could be one argument. I disagree with that. I think that we should really test the limits of computer vision to really identify really challenging attributes, like some of these here. So really, why did these attributes come about? So they were actually built out of kind of an aircraft identification guide. So WEFT, it's called. So wings, engines, fuselage, tail. So when you're trying to identify an aircraft from the ground, you can combine these together. And then if you know certain distinctive features, maybe you can estimate what type of aircraft this might be. So we really tried to flip that around and apply this to an overhead perspective. And that's really why we ask people to label all of these different features. The second really side benefit of this is just creating a bunch of different classes. So with our software that we've released that you can find on GitHub, you can actually combine these attributes together. So if you want to find jet aircraft that have straight wings, or a certain type of propulsion, the number of tail fins, you can really combine all of these together. And this maxes out at 110 unique classes you could ultimately create in the real data set with all of these different combinations, which I think is really interesting and can be really challenging for computer vision algorithms to take that on.
So you're really basically just trying to push this. This was an exercise to push and understand the parameters of the synthetic data and the whole parameterization and all that. Now, one of the key things you're doing here is a concept called transfer learning. Am I right?
Correct.
Do you want to quickly talk about, Thomas, do you want to just quickly describe transfer learning and then also talk about, with the 10 variables, does that make transfer learning harder because you're trying to make things a little bit more, a little bit too articulate?
Yeah, sure. So, transfer learning is one of the core idea at the base of deep learning, and especially for computer vision, right? It's the idea that you can train a model on a particular data set and use that pre-trained model for another task. And by doing so, you are reducing the number of data needed, and you are making the model converge faster. And it's a really powerful idea because as computer vision scientists, we actually rarely train a model from scratch. Like we rarely train a model from randomly initialized weight. We always use, pre-trained model. And so, that's one of the idea here is, we think that synthetic data is going to be useful to creating like really strong prior models. So, by training model on synthetic data, we are creating this pre-trained model, right? Then we can use for fine tuning on a really small subset of data, right? So that's I think that's one of the core idea highlighted by the paper.
So Thomas, with the data and the fact it's got 10 attributes, and then again talking about transfer learning, can the number of attributes affect the transportability of the transfer learning or into other applications or not?
No, I don't think so, Serge. Because of the nature of transfer learning, what we are doing is we basically training this model on the synthetic data set, and we are using this model as a prior for the fine-tuning experiments, basically. And so when doing transfer learning, we're using the pre-trained weights of the model trained on the synthetic data, right? And so we're transferring those weights to for the fine-tuning experiments, and the weights that we transfer are mostly the weights of the model's backbone, and so these weights are focusing on detecting kind of like high-level plane features. And I don't think the fact that having such a detailed data set is going to affect in any ways the transfer learning process.
So it provides a straw man, essentially. I mean, that's sort of, if you're trying to get this for a more business audience, it's essentially the transfer learning is, it doesn't matter about the attribute stuff, because you're creating that framework, and that straw man, which you can then build your classification.
Yeah, correct.
Got it. Excellent. So that's great. Thank you. So we'll talk about your experimental approaches in a minute, but did you try different levels of each out? Did you try with mostly synthetic data or mostly real acquired images and tagged?
Sure, yeah. I mean, there are multiple ways of like combining synthetic data and real data. For example, you could just mix them during training instead of doing fine-tuning experiments. And then what we're trying to highlight with this 10% subset, I mean, obviously we try with like different percentage, right? But we are trying to show that you only need a very small subset of real data. Because of the power of transfer learning, you only need this like really small subset of real data to get performances that are almost on par. So obviously we experimented with different approaches and different way of combining and different hyperparameters for this experiment, but we landed on this 10% subset because I think it tells the best story about how valuable synthetic data is as a prior in that particular case.
In defining this, your experimental parameters, I mean, one of the goals of the system was to find and spot planes which are rarely seen, right, Jake? So can you talk about a little bit about the experimental parameters here, which you already, I mean, I know that you got details in the downloadable case study for people, but just a quick overview of your experimental process here and how you found the different equilibrium points and
Sure. Yeah, sure. So yeah, I mean, we tried several different approaches, really kind of similar to how Thomas described it, with different blends of synthetic and real data. Should you train together? Should you train separate? A lot of our findings found that you should really separate out synthetic and real data during our training process. That might be just really true for this data set or overhead perspective, perhaps. But others have certainly had success with blends of synthetic. We found typically that more is better, especially if you're doing it at the very beginning of your pipeline with this transfer learning approach. We did try another approach where we kind of used less and really targeted our classes of interest at the end of our training pipeline. So we trained on real data, trained on a subset of synthetic, and then we trained on our real data again. And we found that was pretty effective for boosting just our classes of interest. It didn't provide an overall performance boost, but it was helpful for classes of interest.
And so talking about synthetic data sets, are synthetic data sets for general training very prevalent out there, or is this a brand new field? I mean, so.
Yeah, I think the idea is actually, the idea of using synthetic data is actually fairly old, right, in the field of computer vision. There are really well-known data set out there, and a lot of them are focusing on urban environments. So we can think about, Cynthia or GTA5. Those are like, really famous synthetic data set.
Interesting.
Yeah, and I think right now we are like at a really exciting moment because the technology is catching up in terms of realism, and I think that's really going to help bridging this domain gap between synthetic and real data, because the Unreal Engine and other sort of like technologies is really catching up, and so we're able to create much higher quality synthetic data, and we are able to like bridge this gap between like real images and synthetic images.
Okay, so that's great. So that inspires the awkward question, which is, well, why don't you just use an open source engine or an open engine like Unity and stuff and roll your own? Why should I use AI.Reverie?
Yeah, I mean, that's a very good question. I would say, the level of expertise to be able to recreate such, high detail synthetic words. I mean, it's hours. We're talking about like hundreds of hours of, work to just be able to recreate those like synthetic airports, for example. So, if it was that easy, then yeah, you'd be. They are like basically all these software are open source, right? Like Blender or Unity or all that kind of stuff. But like, if you want to be able to create this like high level detailed word, it requires a lot of expertise, right?
Yeah. So Jake, from your perspective, I mean, I take it you worked with AI.Reverie for the fact that they have these skills, or.
Mm-hmm. Yeah. I mean, I think what really sets their simulation platform apart here is just the ability to accurately recreate satellite imagery. I mean, there's so many different complexities that you have to really consider when you get into this overhead domain. So thinking about the resolution of the sensor, you have to accurately mimic that. You have to think about where the sensor is relative to the sun. So the sun can change positions. You have to think about how seasonality will affect your collects. Look angle will vary. As I pointed out, we have look angles that range between 3 and 30 degrees off angle, so we can get into these very oblique settings. Shadowing will change. So AI.Reverie's platform has already built and developed all of these capabilities to actually simulate satellite imagery really effectively. And I think that's really what sets them apart, their ability to do these unique features.
Got it. So I mean, so that it's been coded, I take it. So that, I mean, you've done planes now, but I mean, I suppose you could do fruit trees or crops or something else in the future, right? It's arbitrary now that you've got most of your game engine built, right? Thomas?
Yeah, correct. And we're actually working on a variety of problems at AI.Reverie, right? We're not only focusing on airports and urban environments and agriculture and a lot of the different projects. So the expertise can be applied in many different domains, in computer vision. So
okay. So Jake, can you just quickly cover a little bit more about the experimental procedure that you implemented here?
Yeah, sure. One of the things that we were really interested in was testing how synthetic data was actually being used by our models. So if you think about an object detection network, really what it comes down to is kind of three pieces. One is just detecting objects of interest. Two is classifying those objects into specific classes. And three is just kind of localizing your bounding box to exactly match where your object is. And what we found is that synthetic data was used differently by two different networks. So we tested MaskRCNN and YOLO. And with YOLO, it helped boost our recall significantly. So we were able to find objects of interest that we previously weren't finding at all. With MaskRCNN, it actually boosted our classification. So we had already found these objects, but they were being misclassified as different objects. But with synthetic, we were actually able to boost that classification performance and really zero in on the specific types of aircraft that we were interested in detecting.
And with that, do you find that the distribution of the data, the original source data, matters in terms of the results you're getting there, especially for, like, if you're trying to find planes that are rarely seen? I mean, I suppose that's going to cause a lot of problems if you've only got 3 images, etc. But
yeah, I mean, we certainly had a long tail distribution. So, when we present our results, we were really aggregating multiple classes together to investigate, how trends really materialize over the full data set. You can't just cherry pick different aircraft where we only have a few examples. And I think that was kind of the advantage of looking at multiple different classes. That although we had few examples, aggregating them together and creating a larger test set was pretty effective.
And gentlemen, thank you so much for your participation. Now, you're not going away because thanks to the time of technology, we're now going to go to the live Q&A section, and I'll cue me to cue you.
Yeah. Great.
Okay, everybody, I think we're back again now. And my name's Serge Patel, so I think you saw my face earlier, a little bit on. And now, just want to make sure we've also got our 2 speakers, Thomas and Jake. Are you there?
Yes. Hey, this is Thomas.
Hey, this is Jake.
Hey, Jake. Excellent. All right. So I think we had a really quick question, which was I was just seeing online. Somebody asked if we can download the codes. Now, just to feedback there, you'll find the tab for the download codes and actually the links to it right in the middle below. It says attachment. So you click on that tab, you can actually get all the code, all the papers, and other things there. Okay, all right.
Yeah, I think the particular question was about training codes, which we do not provide and do not plan on releasing because we are using an open source library detection too. So everything should be there, and no modification has been made to that library. So.
Okay. Excellent. Well, actually, we've got some really good questions coming in from the audience here right now. So, I'll just repeat it out just for the sake of it because we don't have the video view here. Can you explain again how you do transfer learning?
Sure. Yeah, it's fairly simple. So we selected the synthetic data set. We train the model, so either faster CNN or masker CNN, and we waited for the model to reach convergence and pick the best performing model, and use that as the weights for the fine tuning experiments.
Excellent. Okay, cool. Excellent. Jake, do you have anything to add to that, or?
No. I think that it was an effective answer. I mean, for our approach, it was very, very similar, where we were using, we were trying to investigate the value of synthetic for detecting rare objects, rare aircraft. We ended up pre-training the networks on synthetic data and then switching to real. We also tried another approach where we trained first on the real data set, maximized our performance, then did a fast tuning, just a few epochs on our synthetic, and then another fast tuning on our real data, and found that was also an effective approach.
All right. Go ahead. Sorry, Jake. Sorry, Thomas, you were about to say something? No? Okay, cool. Well, let's go into the next question, which is, and I'll direct this actually to Thomas more, but actually both of you. Did you find that the duration of the pre-training step affected results? I mean, for instance, does overfitting on the synthetic domain create an issue when later fine-tuning on real data? And that's coming from the audience.
Yeah, so that's actually a very, very good question. So I think what the person is asking is, if you train your model on synthetic data for too long, you're going to create, your backbone features are probably being specialized in detecting synthetic only features, and they're not going to transfer well to the real data. And so, one way of mitigating that is during training of the synthetic model is also to keep track of the performances on real data as well as synthetic data. So, that's the issue when you work with synthetic data. You have this risk of like overfitting, and you want to be sure that like you not overfitting the synthetic data. Want to be sure that you're not overfitting your training set. So that's something you want to keep in mind. So it's not necessarily the best performing model on the training set that you're going to pick for the transfer learning.
Okay, excellent. Thank you.
Yeah, and we did a few experiments that looked at that as well. And really, I think we found that if you trained on the synthetic data for maybe about a quarter to a third of your total training time, that was the most effective for us. But again, I think this will vary based on kind of the task you're looking at. This was for a more complex task where we're trying to identify kind of the make of aircraft.
Okay, great. And there's another really good question as well at the moment, which is, what is the process for determining what features in your simulation are important? Jake, I think I want to hand this on to you to start off with.
Sure. Yeah. I mean, I think you want to try, when you're trying to create synthetic data, what we in AI.Reverie attempted to do was really try to create something that was closely mimicking ground truth as possible. So trying to match the spatial resolution of your imagery. So how big each pixel is on the ground, getting several different look angles here. So, we have that wide range of look angles, changing the seasonality. So, we can modify the different weather conditions, the different backgrounds of these areas. And, you kind of combine all of these elements together, you start to create a more and more realistic synthetic data set. And I think as a result, that's really going to be helpful for improving your ability to do transfer learning and your overall performance. Okay, that's great.
I actually noticed that on the simulation video of the airport, you had a lot of things going on. I mean, you were actually simulating right down to the behavior of the planes, where they were taxiing, they were moving around, you had clouds, and a lot of movement, and that's a lot of detail. So can you just elaborate a little bit on that and about, that level of detail, and especially behavioral detail in synthetic data sets? Because you're still producing some static images, but you're putting a lot of work into doing the actual simulation.
Yeah. So correct. I mean, I guess what part are you interested in more? Because there's so much going on in this synthetic world. I'm happy to explain a little bit more, but is there anything in particular?
I think it really is. You're putting in, my question on my part would be, you're putting in a lot of work into building the simulation and actually even putting in the data for the behavior of the planes, etc. But yet you're producing static images, which are going to be put into a training set. So what is the reasoning behind doing that level of detail in the model?
Yeah, that's a good question. I think the idea is to be able to capture a snapshot of the real world. So, I think it's very important to be able to model planes' behavior. And, once again, we're talking about airports here, but, especially for other environments that we've been working with at AI.Reverie, like urban environments, when you have cars and people, it's very important to have this interaction between objects and this motion implemented. So, when you take snapshot, this snapshot actually as realistic as possible, and, you're able to see the object moving in the environment. And even though it's like, as you say, a static snapshot, I think it's important to be able to, if you want to capture the full variability of the world, to implement those motions. So, and luckily in the case of airplanes, it's actually, probably one of the easiest projects because, the way airplane moves around is actually fairly simple in comparison to humans, for example.
I see, that's excellent. Okay, excellent. Now let's just let's see, we've got a few more questions from the audience. Okay, we've got one here from the audience, which is, hi there, I want to ask a question. When I checked out the data set, it looked mostly like the sat images were layered beneath in the synthetic images. In the paper, you mentioned that one part is fully synthetic locations, one part semi-synthetic, and one part real images. Could you elaborate on how complex it was for you to build fully synthetic data? Looking at the scale, it must be incredible. So I think it's sort of kind of related to my question a little bit, but actually it's a little bit more detailed.
Yeah, so that's a very good point. As the user is asking, the data set actually contains, the synthetic data set has this background of like real satellite images, and we also have fully synthetic world. I'm probably not the best person to say which one was more complex, but from talking with my colleagues, it seems like overlaying real satellite images was actually fairly challenging because you want to be sure that you're aligning the synthetic buildings and the underlying real satellite image. But as far as like generating more buildings is actually something that we do fairly easily. So I wouldn't think that the fully synthetic data set is more challenging. I would say it's probably equally challenging to generate both data sets.
Yeah,
Okay.
yeah, I agree with Thomas's assessment there. I mean, I think creating the real data sets, it's really just more of a time component. I think the synthetic, when you're creating a synthetic data, it's all about creating that engine and making it as good as possible to mimic the real world. But once you have that, you can really create unlimited synthetic scenes. The real data is always going to be manual intensive to do the collection, acquire the imagery, and then do the annotation process. That doesn't ever really get any faster.
Excellent. Okay, so great. And actually, we're getting some really interesting questions coming through, which is around about the modeling and around that. One very simple question, but depth and answer here is, where did you find the synthetic data to fall short compared to real data? Is it in the recall, the precision, or both? Let's say, Jake, I'll start with you, Thomas. Yeah.
Yeah, I mean, both Jake and I can answer that one. I mean, we run different experiments, but, overall, I would say that synthetic is, in terms of recall, we were actually getting much better results in comparison with the real experiments than in terms of precision. So that's fairly interesting. and we learned a lot by iterating on this RarePlane dataset, the RarePlane synthetic dataset. So, we learned a lot about what feature of the dataset needed to be present to get better performances. For example, different types of plane models was actually very important to add more diversity in the plane models versus like weather or biomes. It was also very important to keep adding more diversity. So yeah, in short, recall was close, good performances in terms of recall and a little less in terms of precision. But Jake has different results, I think. So.
Yeah. I mean, just kind of thinking back to our results, really thinking more about just kind of looking at if you trained on just real data or if you just trained on the real and synthetic data, if you augment with synthetic. We found that for one of our models, for YOLO V3, it boosted recall significantly, but for MaskRCNN, it helped boost precision. So it's kind of an interesting trade-off there, and I think it really comes down to how these object detectors are designed and really how they make their proposals. I think MaskRCNN is a much more complex proposal network than YOLO. But yeah, I think it's something that really requires a little bit more research.
Okay, excellent. So, okay, go on. Did anybody say there? No. Okay. So, let's just take a look at any other questions coming in from the audience. And so we got another great one here. Suppose synthetic data was not available. What would be the time in total to gather the real data and annotate? So I suppose that we're really, so they're asking a question I think we asked a little bit earlier in the video part. But Jake, do you want to answer this one? How much would it could have cost you to do this with real data, and how long?
Yeah, this project was about a year and a half long. So when you get, when you're buying satellite imagery, you have to consider a lot of different things. You have to consider, just like the licensing, the purchase price. There's a lot of negotiations that go on up front just to get that data. And then beyond that, you have to consider the annotation time frame. So we selected all of the images, and we sent them away for annotation. Ultimately, that process took several months. Then we had quality control following this. So really to create a data set of this scale, you're really sitting at several months of work. I would estimate it between 8 to 9 months to recreate something this large. So yeah, a very significant time sink to do that.
Okay, excellent, great. We actually have a follow-up question to the longer question I just got earlier. I think it's the same person. Just so the audience knows, we don't know who asked the question, so we can't attribute it to anyone. But I'm going to assume that this is from the person who asked the question about, the longer question about the modeling. So the follow-up question is, do you think it is more difficult for different domains? Satellite imagery is probably super detailed, versus I saw on your webpage some till sorting. I think that it is probably super promising for you guys. Will you open the data sets to the wider public as well? As a researcher, it would be awesome to buy or access the synthetic data set. So I think what they're really asking is, will they be able to access other data sets in the future? And let's actually, I just saw there's like 3 or 4 questions put in here. So let's answer the first part, which is this more difficult for different domains?
It definitely varies from one domain to another. This is definitely, I would say, one of the hardest projects that we've been working on. But we are working on a variety of different projects from, in agriculture, for example, which it's a little easier because we don't have to model as much details. And, we also worked in non-RGB domains. So we worked on some project where the data that we were modeling was not RGB images. And in that case, it's actually also a little easier. So, it really varies. But for example, when we work with urban environment, then it gets, in my opinion, a little more complicated because you have to deal with all the objects' motion and interaction, and it's much more complex than airplanes. So, it varies. As far as like making those data sets available, I think, so obviously, the RarePlane data set is available. I think it's going to be an ongoing project. In partnership with CosmiQ for the next, months and years, we're going to iterate on that data set. We are probably going to release some other data set in the near future, but this is something that we're thinking of, and nothing is clearly established yet. I would recommend to reach out to hello@AI.Reverie.com. If you are interested in buying or accessing some of our synthetic data. So I would just recommend to reach out.
Okay, excellent. And actually, I was just going to encourage the audience actually into this, the part where it says ask questions. If you guys have requests for any specific types of data sets, synthetic data sets or augmented data sets with synthetic, put them in there and we'll make sure we grab the information for our product managers. Now, going back to the questions, actually going back to the main question, hang on, it's just moved. Because there was the first part of the question, the second part is, let me see. Okay, yeah, no, I think you answered it, which was, will you open the data sets to the wider public as well? That's great. Okay, so with my question related to that is, what is the license on this data set? Just so that people know, what can they use it for, what they cannot use it for? Jake, do you have any answer on that?
Sure, yeah, so it's a CC by share like 4.0 license. So yeah, this is a very permissive license. So if you work for a commercial entity, you can use this data set. If you're an academic, you can use this data set. The only thing that's really required by this license is just attribution. So you just have to cite that we use this data in our work, which is a very low bar. So we like to open source data sets like this at CosmiQ Works because we think it's important for driving not only academic research, but also commercial ventures as well. And we're excited to open source it this way.
Excellent. Okay, thank you, Jake. Thanks for that. Okay, we got some really good questions. We have a very informed audience here, which I love. So the next question is this: have you explored the effects of using curriculum training methods on model performance? So, Thomas.
This is not an approach we have experimented with.
Okay.
I'm going to be honest. Yeah. I think the idea with this paper was really not algorithm oriented. It was really focusing on the data set and the value of data. So we didn't really apply any. And I think I'm going to actually answer also the question. There was a question regarding domain adaptation techniques. So I'm going to answer that one in the same time. Like, we really did not focus on any domain adaptation technique, whether they are, at the image level, for example, CycleGAN or other image-to-image translation method, or, the feature level adaptation. There's a lot of research in that area right now. So, we really didn't want to spend time on this because we wanted to highlight the value of the data set by itself, and showing that, good synthetic data can actually provide like very good performances without any extra effort on the algorithm side. So yeah, I think that's the answer to my question. So we really didn't put we really didn't explore much like algorithm side. We were focusing on data. So.
Okay. Okay, great. Jake, do you have anything to add to that?
Yeah, I mean, we'd encourage everyone to try out domain adaptation approaches and report your results.
Okay, thank you.
No, it is
All
a
right.
great answer because, that's the whole point of making this data set public, is because we want people to explore, and use it for research. So go for it.
That'd be great. And can we feed back their results through AI.Reverie and through your team and guys as well? So collaborate with you guys on that, Thomas.
Sorry, I could not hear you for a minute.
Okay, I was just going to ask is, if people want to collaborate on data sets like this and on any other sort of future things, can they reach you at hello@AI.Reverie.com?
Yeah, correct. Yeah, just reach out to us. We are always very excited to work with new projects, and we have, a lot of expertise in working in very different areas. So we'll be really happy to collaborate on any synthetic project.
Excellent. Thank you, Thomas. All right, so back again to this idea of synthetic data and real data. There's a good question here. Can we train only using synthetic data without any real data validation? And if so, how do you know that you've created a world that is good enough? So that's actually a great question, actually. I mean, I'd like to direct that one to Thomas, please. So you go make a world, how do you know the world is good enough?
So, yeah, it's kind of hard to answer that question, because I'm assuming, if the ultimate goal is actually using the model on real data. So if you do not have any real validation data, then you're never going to be able to estimate how good your model is, and you're never going to be able to, know when you need to stop training or know when you have enough data. And so it seems it's a little hard to answer because of that. As far as like knowing when the world is good enough, I think this is much more interesting because, as human, we tend to think that, we tend to see the image in a certain way. We tend to aim for a lot of photorealism and think that like something needs to be perfect. And especially, when you work with the people at AI.Reverie, those very talented technical artists, and they want the data to look as good as possible. But sometimes like it doesn't mean that it's actually going to improve the model performances. So there's actually a lot of back and forth and a lot of iteration between creating those data sets and checking the performances. So I would say give us your project and then we can create the world that would be perfect for the application that you're trying to the problem you're trying to solve. So
okay, cool. Actually, just related to that, I'm going to put up a question here, which is from again, it's sort of streaming in from the audience now. So the question from the audience is, okay, are we overrunning a little bit apparently? So I'm just going to ask this one very quickly. Do you draw a line when synthetic data is better, good enough for a case, or do you have to do it on a trial and error basis? Basically, iterating on a certain level of detail is sufficient.
Yeah, it's another very good question, which is it's interesting because that's the whole process that we went through for the RarePlane dataset, right? So yeah, there's definitely a point. You're definitely plateauing at some point where especially when you do more fine-tuning experiments, where you reach a level of details that is, it's going to look better and better. And like if you were playing video games about airplane, then that would be great. But as far as like performances of a computer vision model, it's not really going to improve. So it's as of now, it's a little bit of a trial and error, and we're working on improving this so that we know what level of detail is necessary. But it's really project specific, so it's hard to answer.
Thomas,
yeah.
Jake, we are about to end soon. I just want to thank you so that the audience knows that we didn't just get cut off. And we have a few more questions here. And I think what I'll do is I'll try and save these questions and see if we can answer them on the AI.Reverie blog, which I encourage everyone to go to and sign up for the newsletter. And we'll take these questions there because there are some really good ones here about looking at that. And for the gentleman who works with the rental car company, yes, we do contracted work. Why don't you reach out via hello@AI.Reverie.com, and we'll talk to you soon.
Thanks, everyone. Appreciate you tuning in today.
Thank you so much, everyone.
Thank you, Jake. Thank you, Thomas.
Thanks, Serge.